Happy Wednesday, everybody. Thank you very much for taking the time to join me in this e-presentation. I am Mohammad Samsud Joha and I am here to talk about our work on mobile app analysis, which is summarized in the Rene paper titled Checking App Behavior Against App Description. What if there are no app description? This is a part of my ongoing PhD work supervised by Professor John Grundy, who is an Australian laureate fellow and professor of software engineering at Monash University. Dr. Lee, Dr. Huri, and Dr. Kung are my co-supervisor. We are supported by research funding from ARC, Data 61, and Monash University. Today, I will start off talking about the key motivation for this research project. Then I will talk about how we try to address that problem and how does our approach performs. I will finish up summarizing some key discussion. Okay, starting off, currently around half of the world population had a smartphone. As we know, Android is the most popular mobile platform and Google Play Store is the official pre-installed app store on Android certified devices. And authentic statistics reveal that more than 1 million Android apps were removed from Google Play Store in between 2018 and 2019. These apps were removed because they were flagged as malware or contain anomalies. They did not behave as advertised. They had low quality and design inappropriately. They violated the publication policies or were miscategorized. Several research efforts have been conducted to address this problem mentioned above, especially malware or anomaly detection through classification. The most popular approach, such as Chavada, extract the topic from the app human authored description and build a related app cluster. Then sensitive API uses for that cluster is grouped. Finally, if an app use any sensitive API that are uncommon for its corresponding cluster, it is marked as outlier for further analysis. The main strength of Chavada over other approach is that it processes very lightweight information. However, if the description of the app changes and or unavailable, the information that Chavada has for that app is no longer valid. Moreover, many app descriptions do not reflect app functionalities, whether accidentally or on purpose. Most importantly, these methods do not work if the app description is unavailable. Therefore, our reverse engineering based approach called React try to avoid such failure and reproduce the same result as the existing approaches using the data that exists inside the apps. To validate and replicate React, we collect 19,766 Android apps that were examined in the well-known Chavada prototype. We then reverse engineer this app to extract the keyword from method name, XML data value, and text from the image file. The extracted data were then preprocessed and a clean dataset was prepared. The clean dataset is the final input that is used in topic modeling for final classification decision, that is app grouping. Further discussion on React design and working procedure is beyond the scope of the presentation. An interested audience can refer back to the original paper for this. In React performance evaluation, our analysis found some limitation in React procedure, especially for similar feature-based app grouping. But we find the root cause of failure that help us to identify several future enhancement ideas. We also learned several lessons from this analysis, especially for future app analysis tasks, replicating prior work and handling rapidly evolving app version for analysis. The React tool and dataset can be used for different research purposes, such as identifying potential malicious activities in the mobile app. In addition, we also proved the scalability of our React approach over 5,000 apps that have not been previously examined. Let's move to a few final discussion. First, we extract the data from currently available Chavada app. We tried our best to collect the full set of apps but were partially successful. We explain the reason for accepting the partial collection at this stage in section 3a of the paper. Secondly, React is subject to an additional construct and internal validity threats. For example, we remove a set of uninteresting apps before the final classification step. It helps us to prepare a clean dataset. However, it is an intrinsic limitation of the React and it should perform equivalently even in presence of uninteresting apps. Moreover, identifying pattern from existing raw data, including the unrelated and uninteresting app without app removal is an interesting future research. Finally, we ignored the runtime generated data. The dynamic analysis was not used in part so that replication can be carried out without concern about historical app behavior. However, we have learned several lessons. For example, we found data obfuscation and encryption is mostly done on method name and XML data values rather than GUI string in Android app. We also found that two quite different type of Android app can share substantially similar set of XML data values. Thirdly, we realized combining new app analysis data with the manually extracted data could improve the classification of app groups. However, in such case, this method won't be suitable for app whose description changes are not available, as well as for more larger input set. Then React classification result largely depend on the outcome from the LD and mallet topic modeling algorithms, both of which are probabilistic. Therefore, these algorithms return different topic when performing repetition of the same dataset. An interesting future work is to identify outlier from each data type and then classify. Thank you very much for the time to listen me today. I am happy to take a few questions.
Okay, hello again, and thank you for the presentation, Mohammed. Let's see if anyone have some questions. If not, I can ask my question here. Okay, probably I will do it. Do you think that the collection of additional data, such as images or geographical location, will produce a better classification of your model?
Yeah, it's our initial supposition is that when we do some of the additional data, such as image or the GPI data would help. But the problem is that processing this data, image processing is always costly and time consuming. So for a large input data set like our one in the 20,000 Android app, the effort that we are given to prepare this data for a, in terms of the text from for the classification, we hadn't got much. So initial our supposition is that it could help, but we found that does not that much helpful compared to the resources required and the processing time as well, other stuff. So we had pointed out this one into our figure in our recommendation that although we thought that image file and the other stuff is really help, but now it's not.
Okay, I have another question from Anita. So she said, how could the Chabda approach be so popular, given they only look at app description, which malicious developer might lie at?
Okay, Chabada is so popular because compared to the other existing approaches, it is very lightweight. Lightweight means it processes very lightweight information. Only the app description, that means you do not need to have cleaning the data. You already have your text file or the sentences available. And compared to the other stuff, they are processing very heavy data, as we say that processing. So the popularity for the Chabada is main reason is that it processes only the lightweight information to
Okay,
classify whether it's a malware or not.
great, thank you. So if anyone wants to ask more questions to Muhammad, there will be now time. And I can see you in the ICTC social room. Right now